Hi everyone, my name is Jing. I'm currently a postdoc affiliated with Stanford Robotics Center and Stanford Center on Longevity. And I received my PhD from UMD, advised by Professor Dinesh Manocha. It's an honor to talk about our prior research today here. So in this talk, I'm going to introduce our prior work on robot navigation, and later I will also talk about our current work that we extend this navigation stack to companion robots for older adults. So our prior work primarily focuses on robot navigation. And the question is, what is robot navigation? Robot navigation is a process where, given a goal, a robot will plan a path and autonomously move to the goal. The robot navigation also has a really big impact in our lives. And especially for outdoor applications, it's revolutionizing the logistics, and the last mile delivery robots can make the essential goods more accessible and convenient to everyone. And for indoor applications, the warehouse robots can drastically improve the efficiency and safety in warehouse management. And they transmission human work from carrying and lifting to managing and supervising. So ultimately, by offloading the tedious and risky tasks to autonomous agents, we can release ourselves and we can free ourselves to focus more on creative and high-value works. But robot navigation is challenging, especially in outdoor environments, because outdoor environment is very unstructured. And the first challenge is that robots is not just avoiding obstacles, it also has to identify and understand the traversability of the terrains. And another challenge is that the robot has to keep socially compliant to pedestrians, and the robot navigation needs to keep pedestrians feel comfortable and also less disturbed. And besides this, while the robot is moving in traffic, it also needs to understand the traffic context, such as the traffic lights or the right-of-way rules by interacting with pedestrians and vehicles. So our research focuses on addressing all those challenges. So how do we know where a robot can go? Well, for different types of robots, their traversability is quite different. For wheeled robots, they require flat and continuous surfaces to move on. But for legged robots, curbs and stairs are also traversable. And as shown in the picture, the unstructured vegetations could be obstacles for small robots. But for big and heavy robots, those areas could be traversable. So the robot has to identify its traversable areas and generates feasible trajectories or actions to drive through. And one of the very straightforward way is to directly generate trajectories for the robot to follow. So in our work, we generate trajectories to cover the traversable areas around the robot by using an autoencoder and decoder mechanism. And we linearly project the intermediate Gaussian distribution to orthogonal axes to generate multiple Gaussians. And each of the projected Gaussians corresponds to a trajectory. And we can also use Hausdorff distance to train the trajectories to be diverse enough to cover the traversable areas around the robot. So we got the multiple trajectory candidates, and then we label them with numbers according to the distance to the robot. And then we use vision language models to select the best trajectory to achieve the goal. This video briefly shows how the pipeline works in navigation, and the red trajectories are generated candidate trajectories, and the green trajectory is selected by the vision language models. And this video shows the comparisons among different learning-based and vision language model-based approaches. The convoy is purely based on VLMs, and it asks VLMs to select the direction to go. Nomad is learning-based approach, uses pre-collected topological maps. And MTG is our approach without using language models, and the trajectory is selected by the shortest distance to the goal. And in the video, each of the red clip is human interference. And we can see that our approach is relatively good in general, to detect the traversal areas and move the robot. But still, it has some out-of-distribution situations where the trajectory candidates are not well generated, or the robot cannot follow the trajectories really well. So we can see here are some red clips in the VLTGS. This is an unknown issue, and we still couldn't figure out why. But it was solved after we got extensive trainings. All right, so to train the model more generalized, we introduced a navigation dataset, which contains 10 campuses and 11 hours raw specs. And each campus has a global traversability map with 5 categories of traversabilities. And the users can correlate the robot positions and observations with the global traversability map. And in the dataset, we collected multiple modalities of sensor data as well, including the 3D LiDAR, RGB, 360 camera, MU, GPS, and odometer. So you can show the data visualization in the George Mason campus. And, but in the previous structured environment with a very clear pavement, the robot only needs to follow the pavement. But when a robot runs through the off-road unstructured environment, the definition of the obstacles could be blurry. And the robot needs to understand the semantics and also the physical properties of the environment, such as if the grass is pliable, if the bushes is traversable, and if there are stones or trees that are obstacles. And in our work, we leverage Gaussian splatting methods to render the environment around the robot with semantics. And to make the local map more accurately represent the geometric shapes of the environment, we also fuse the LiDAR information by Euclidean side distance field. And then we integrate all the maps together and get a local map for planning. But the semantic information is not sufficient for the robot to understand if the terrain is traversable. For example, as shown in the picture, the robot needs to know if the vegetation is pliable for the robot to drive through. So on top of the Gaussian splats, we jointly estimate the semantic material types and the physical properties. The physical properties include friction, hardness, stiffness, and density. And they are estimated by Dirichlet categorical posterior. And the semantic material types include grass, trees, buildings, and etc. And they are estimated by Gaussian posterior. So from the robot observation, we can generate a local map for planning. And in the local map, we can see that the red color indicates the non-traversable areas. And the green, blue, and gray points are all Gaussian splats. So from the video, we can see that using the Gaussian splats map, we can plan a path and move the robot through the unstructured vegetations. And as mentioned earlier, when a robot is moving in a crowd, it needs to move socially compliant to pedestrians, such as not intersecting groups and not racing against pedestrians. And the goal of the social navigation is to make the pedestrians feel safe and comfortable. And also, when the robots are moving on straight, it also has to understand the traffic conditions and follow the traffic rules. So the challenge is, how do robots move compliantly to social and traffic rules? To address this challenge, we decompose the task into 3 steps. The first step, perception, is to identify the pedestrians and groups and understand where they are moving and their relative positions to the robot. And the second step is prediction. So it has to predict the motion of pedestrians and the potential interaction with the robot. And the third step, action, is to tell the robot how to move with regard to the social and the traffic conditions. And because the recent development of vision language models has made has made a really substantial success in understanding the context of pictures. So in our work, we also leverage VLMs to understand the social and traffic cues. And we created a data set for social navigation with language context called SNE for training and evaluation purposes. And we evaluated ChatGPT, Gemini, and we also fine-tuned the Lava with the training data set using low-rank adaptation. And as shown in the radar chart, we can see that the fine-tuned Lava is generally better than other models in all three tasks. And the Gemini works better than ChatGPT in all the three tasks. And it's also very comparable to with the fine-tuned Lava in predicting pedestrians' behaviors. And after integrating all the previous works together and combined with GPS routing and low-level motion planning and control, we have the navigation stack for general outdoor navigation purposes. And this video shows the navigation performance with various robot platforms, including lagged and wheeled robots, and in different county and city scenarios. We can see that the robots can keep moving on pavements and sidewalks, and the robot can also follow the traffic rules to go across the street, and they can compliantly interact with pedestrians. And now, in Robotics Center, we would like to leverage the robot navigation and extend the previous navigation stack to companion robots for older adults. And this shift requires the robot not only navigate by itself, but also serve as a caregiver to provide advices and assistance to interact with human. As shown in the figure, by 2020, over 55 million people in the United States were aged 65 and over. And according to the prediction, more than 20% of the population will be senior adults by 2030, which means that for every 5 people, there will be 1 senior adult. And we hope our work can contribute to improving the life quality of the millions of older adults. As we age, our vision may dim, our hearing may fade, and our joints may slow us down. But it doesn't mean that we lose the desire for active, healthy, and socially connected life. And we all want to stay independent, engaged, and vibrant. And this is where our companion robots can step in. So companion robots can serve as an enhancement of our vision, hearing, and movement, and they can be used to assist with mobility, monitor health, and ensure we can continue living a high-quality life. So one of the research directions we plan to do is navigation assistant. We want to create a general navigation stack that robot can serve as our eyes and ears and alert human to hazardous terrains and traffic. And one of the biggest challenges is that we need to create a real-time and also accurate world model to handle all the emergencies and hazardous terrains. And then based on that, we also want the robots to compliantly move alongside older adults and talk with them as a companion. This is quite different from traditional social navigation that requires robots to compliantly avoid pedestrians. This requires robots to adaptively keep the same pace with older adults and receive language instructions and manage tasks and motions accordingly. The second direction is the behavior analysis for older adults. And we visited the Channing House and spoke with the senior community. And we realized that they are really scared of falling down, and they care a lot about their physical health. But at the same time, they also don't want to rely on walkers and other assistive devices. So what we plan to do is we would like to use the robots to monitor their health. And we would like to identify the human motion and correlate the human motion with the potential diseases and risks. And we are also trying to design a platform to adaptively provide sports to older adults, but also give them enough freedom to exercise and walk independently. So on the left, we can see the Jita Mini robot, and currently it can follow humans. And we will also get the unitary wheeled-legged robot soon. So to summarize, we covered the approaches for traversability analysis and understanding the social and traffic rules. And we also talked about our plan for navigation assistant and behavior analysis. So if you are interested in collaborating in any of the research projects, please email us, and you can find my email in the QR code. Go ahead.
That was really cool. It was great to see the stuff you've done before as well. It put me in mind of something we deal with in archaeology a lot, which is this idea of least cost pathways and how we work out what is actually a traversable piece of terrain to a human versus what a machine thinks is the easiest way to get from A to B. And I'm just curious what you think about using those kind of trail data sets that we might use in archaeology that look at, pioneers. So we'll take things like Garmin trail data or National Park Service data of where their trails are and try and use that to replicate the way a GIS system thinks about the park. Is that something that the robot could do, or are you trying to do something that's much more real-time with what the robot is seeing in its position?
So your first question is, what's the difference between we decided which area is traversable and the robot found out which area is traversable and the best path to the goal? Is that correct?
Yeah, basically.
Yeah. So I think mostly it should be very similar, especially for lagged robots, because I think the most important criteria is the safety. And so, for example, if the robot can actually traverse this area without any damage or vibration, right? So I think in this sense, it would be very similar as how human define the traversable. So we also want to avoid risky areas and want to go to the goal, right? But I think in another sense for the planning, so optimal, it depends on how you define the optimal target, right? So for example, if you define the target as the shortest path with like relatively low, like you have some tolerance to the vibration or the risks, right? So it's in this sense maybe it's a little bit different. Yeah.
Any more questions? We do have time, I think, for another one.
All right. Thank you
very much.
So thank you for inviting me here to share my research to you. So my research topic is about from digital humans to safe humanoid. So it's more specifically, we use grounded reasoning in large language models and the compliant interactions towards humanoid. So a little bit context before I come here, working with Professor Catherine Liang in robotics. Before I was more work on how to learn digital humans from daily input, like just to use your phone to take a picture, to record a video, or just give some text. Then we are able to rebuild ourselves in the digital world. So it kind of quite natural for me, like to transfer all the digital world now to humanoid, where I treat the humanoid actually as a ultimate test beds to verify what we've learned for digital human and put it into digital world is correct and in the physical intelligence. And I would say humanoid can also regard it as a data collector, like can help us. It would be a moving camera to help us to collect more human data. So then this could be form a human-centered AI flywheel if we do human-humanoid interactions. So what I've been research a lot during my PhD is we get all the daily accessible data set and learning digital human models, and then we want to like deploy our learned models into the physical intelligence, is like into the humanoid. Then So ideally, I hope like if we really have a good and reliable humanoid that can really into the human space interact with us, it can kind of have a good feedback return to help us collect more human data. And then could be a flywheel to get better data, to train a better model, to have a better humanoid can interact with us. So then we need the robot into our human space, into the real world where our humans are everywhere. For that, then there will be a lot of applications, will be assistive support and healthcare applications. And all this, we can say common point is there will be physical contact. And for this, we can see a lot of humanoid robot, for example, Jing here, and can perform some motions well. But the problem is if there is some physical contact that is not expected, that might be very dangerous. Some unexpected behavior will be there. So towards this problem, like I like to talk about the first work about GentleHumanoid, where we try to learn the compliant human control for safe interactions. So let's work together with Professor Carnew and the amazing student, Chinzo Liu. And before that, talk a little bit about now the general pipeline for controlling a humanoid robot. Normally, we just train a motion tracker with RL policy. So stage one is like we can have a lot of human motion data set. Normally, this is from either mocap or also can get some from the video data set. Then second stage, we can train a universal controller in simulator, for example, normally in Mojoko or AskGyms. And once they are policy is trained, then we can apply that into real world where we give a reference motion, and then the humanoid can act like the real human to control it. But the problem is we want the humanoid not just following the reference motion, but also regulating the interaction force. So the goal is not just a general whole body motion tracking, but also with compliance and also trainable forces that could adaptive for different human interaction tasks. So the compliance that we hope the robot could adapt its motion like safely, like when unexpected external forces occur. And trainable force is we can control how soft or how stiff the robot behave. For example, for assistive tasks, we want the robot to help set to stand task. We want the robot arms to be stiff enough to support enough force. But for like some interaction, we want shake hand with robot. We want G1, the hand, to be soft, so we are able to shake it. So how do we do that? First, about compliance, we do this from force modeling. So we regard motion tracking problem as using a spring damping system to model as a driving force, and we model the interaction force in two kind of things, and then we have the robot movement is combined by the driving force from motion tracking and the interaction force like modeled by our system. The interaction force we separated into two scenarios. First is resistant contact. It will happen like when robot itself will press against an object. For example, I'm a robot and I'm walking, and my hand maybe will touch the object, and at this time, like we want my hand to stop when we like just touch the object. In this case, we just produce a force like separate to these directions to kind of compensate the driving force. So it will just stop right before just in this object. Another force modeling is guiding contact. That is, the force will produces by another human. For example, I'm walking and another person is just trying to dragging my hand. In this force, then we model this kind of guiding contact force distributions from a data set. We use InterX, it's a human data set where we can see a lot of human motion distributions when we interact with other people. So here, what we can sample is there are a lot of motion distributions from upper body where we can sample between two poses. We calculate the positions and it can produce the driving guiding forces to drive the position to move. So for these two forces, then we can have a compliant training. Then we want to control the force limit. For example, like when humanoid interact with human, we don't want the humanoid to produce a force like larger than 20 newtons that might hurt the people. So for this, we have a formulation like we limit the driving force like produced by the motion tracking to be under the safety limit. Like the limit could, if lower limit, it could yield a softer and safer behavior, and a high value allows more firmer support. So with this reward together, we integrate all this into the general motion tracking pipeline, where we also use the dataset from MS and InterX dataset together to learn the distribution of how human-human interactions and to train the universal policy. So the route could be, for example, the right is the reference motion, and actually in real world we are able to either drag the hand and play with the arms with G1, and it's still very soft and still robust and still very safe. And we can also tune the safety threshold where the robot can produce different forces. With a lower threshold, we can say it's quite soft, and with a higher threshold, we can feel it's more stiff. So we also have a real-time demo for it. So this real-time demo where we can drag it and we can adjust the force limit and play with it. So it's kind of real-time demo where you can just visit the website and play with it. You can also choose or upload your own motions to play with it. So during working, you can play with it anytime, and it is still stable. It will not fall over. Done this. Okay, cool. So the applications like we can have, there will be a lot of humanoid interactions. For example, like set to stand assistant, and also we can play with it, and we can win when doing this. So this will also help with human object interaction applications. That's the example, like we try to record a video and where we reconstruct the human motion from this video as the reference motion. And from the same reference, we can make the humanoid to interact object with different size, different ways, and it can still follow the reference motion well. Especially for the balloon case, it's actually quite soft, hard, very difficult to handle. So we also set up a new evaluation setup. So we collaborate with Professor Zollenbaum's group, where we use their advanced sensor pad, and we attach it to the mannequin, and then where we can say when we touch it, we can visualize the forces, the pressure in this place. So here we compare to other the vanilla RL policy and the extreme RL policy, where we trained with extreme force computations. So here we can see the curve here. Actually, our curve is the blue one, where we just consistently produce a very stable forces when interaction with humans, with many fake humans. Yeah. So based on this, our control policy, we also build a vision-based pipeline for better hugging. So that is, we add a camera on the top of the G1 and then take a picture. This is actually me, and it can actually estimate the shape and then optimize the hugging to better hugging. For example, people want different height, we might, the waist position is different. We need to optimize to make the human feel the hugging is more comfortable. And they route like this. So it actually feels very good to hug a humanoid. So actually, we can say for different person, we have different height here. So then we face another problem. So for this pipeline, the intention is actually manually scrapped. So we ask G1 to work. You need to work towards a person and perform hug. But ideally, what we want is, can G1 decide this on its own? So it can decide, like, to understand what the person in front of G1 is, what their pose and their motion and their intent, and the reason about the context. Should we hug this person or not in the scenarios, and applying the next action? For example, what the exact hug style should be, how tight the embrace could be, what's the exact body configuration. To do this, normally the large language models we treat is a mind. However, the limitation is normally it's described as text, and not cannot recover the 3D configuration. So if we explicitly ask large language models to produce the key points or the 3D poses where humanoid can track this reference motion, and it's actually this route, and I try to visualize, it's actually quite wrong. So for this, I will talk about two of my works. It's about how to utilize large language models for human behavior understanding and planning. So one of the work is about ChatPose. So we kind of inspired how large language model combined with vision is. So from text input and image with large language models, and where we normally, for example, for lava, it actually uses a projection layer to map the image space into the language space, so large language model can better reason about it. So the similar idea can also treat human 3D poses as another modality like image. So for this, we also train a projection layer where from large language models it produces language tokens, and from this token embeddings we also train a projection layer to directly output the 3D body poses, where we use the simple pose is parametric body models. So then we fine-tune the large language models where we use LoRa fine-tuning, and also at the same time train this projection layer. The data to train it is we use similar to Lava, the instruction following dataset, where we make it should still keep its general reasoning ability. And then we use some dataset from human pose estimation from image, and some dataset from human pose generation from text descriptions, and all this multimodality dataset called training. And then after that, the prior from the best models could do something that training data cannot say. For example, for training data, mostly we use cropped image to pose, and we use detailed text to pose. Detailed text is about really specifically describe where your arm is, where your knee is, rather than some high-level implicit descriptions. For example, like a man is posing, there's actually nothing about descriptions of the exact pose, but it can infer when proposing it should, how about the needs should be, and to this, and it could react. So the route could be, we can directly chat to these large language models to ask about what's happening in the image, for example, the pose, and the large language models can directly produce the pose, the 3D pose, and visualize it. And we can further ask about the intentions to predict the next move. So at this time, and the large language models can also directly output, they produce the movement. So, but the problems just now, the work is about human poses, and there's more than just a pose. There's also, we need motions for humanoid motions. We also need to understand the human's biomechanics, how tall it is, what's the emotion it is. For this, we have another work, ChatHuman, where we use a large language model as an agent to read all the 3D human related papers and to know how to use these tools to solve problems. So it's kind of one system for all the 3D humans. So the route can be like the read papers and find optimal tools, and we can have demos like could estimate the 3D bodies, what's the height, what's the poses it is, and we can also generate the exact human motions, where the kinematic motion can be used as reference motion for humanoid to behave. And also there is expression state. So one of the applications for robotics could be like, imagine this image is the humanoid can see, and we can actually estimate the exact hand poses, and we can also further ask about ask it to predict the next motions. So it could be cooking will be like this, motion generated. So also to understand like how human behavior, like the safety issues, to observe, to decide what to do next. So far, so we'll talk about GentleHumanoid, where we can track any kinematic motions with compliant control. We also have ChatPose and ChatHuman, where we can find image or find language we can understand and reasoning about to produce the kinematic pose or kinematic motion together. So it sounds like to connect these two, we can have a good pipeline for humanoid to interact with human. However, there are still challenges and open problems about, especially for system design. It's about we need real-time performance. Since ChatHuman ChatPose is based on large language models, there's still a little bit delay, maybe 1 or 2 seconds for inference. But for robot, we want it to be real-time. And also to work with dynamic humans, we need like metrically accurate understanding, like how far the distance it is. Also, it's about active vision, also long horizon task. And what's these two are actually, I have ongoing project working on this. And if you want to collaborate, also please, like we can talk offline. So also, we can think much more about future direction. Just imagine a much more challenging case. For example, nursing robot. So perception, there may be beyond vision. We need tactile, like thermal, for example, to a nurse to help about shower. Then we need to feel the temperature of the water. Then by mechanical states, we want the estimation is not about just healthy people. Also, especially in hospital, there are a lot of people with mobility constraint. And for reasoning planning and how to do this, we can think about how to align what we need to have in social scenarios, like some metrics like being empathetic, helpful. This kind of maybe reward to fine-tune like VOM to being like that. And the more actions is not just the actions, like maybe we need more multimodal expressions, like we need to coordinate voice, haptic, and also maybe facial emotions that can support, give more emotional support, and also hardware interfacing. Okay, and kind of callback to the flywheel. So once we imagine we have that, maybe next we think about more how we use humanoid to collect data for us. So that's it. Thanks for my all collaborators, and thank you.
I have one question. So for your future direction, these are pretty general directions. Are you thinking about a particular problem, a field of problem, like is it for mapping emotional media to robot, or sorry, robot control, or any in general? What's the specific field?
The specific field for future directions?
Yes. In your previous slide.
Oh, this one?
Yeah.
Yeah, I will. Actually, specifically, I want to focus more on reasoning and the planning part, like how to make human, like the kind of social brain, like to work, like to better interact with humans, like especially like being helpful some principles to help training large language models to better interact with humans.
So it's like collaborating more.
Yeah. So there's a lot to do, and also about biomechanical states of it. Since my previous work, it was mainly about building the digital model of humans, especially for like from large-scale dataset. I want to build a better state, but like people with mobility constraint and emotional state are still missing a lot. I want to focus more on that, and so it's better for humanoid to interact with people.
I ask one more question. So in your first work, you have a policy that can make a humanoid compliant. You have demos where you can drag the robot's arm. The robot can move around, respond to external force while still maintain stability. I missed the point. How do you train the controller? How do you obtain the controller that does both the compliance control and the body balance?
So for make it compliant is from this formulation we can calculate a new reference motion. And this new reference motion, since it's already after the compliant calculation, so to track that, so it can already be compliant. To make it in the bind is, so we design it as a reward. So it is we add a penetration. It is if the interaction force is bigger than the threshold, we have a kind of things to make sure it is not larger than that. And when training, we sampling different threshold, like between 5 Newton to 15 Newton. So it can say a larger of force bands between this range.
I see. So it's our policy.
Yeah, it's our policy.
Okay.
Yeah.
Okay. And do you have those virtual screen models explicitly during inference, or do they only exist during training?
Only in training.
Okay.
Yeah. We hope it's like in training it can learn enough distributions about the forces and the interactions. So during inference it kind of explicitly kind of predict what to do. So it can be general, like it's a universal policy, like can work on any reference motions.
Great. If we don't have more questions, I guess we can thank our speaker again. Thank you.
Thank you.